Okay, yes, I do have a new pen, and we will just hope that it works well. I don't have a backup battery. I didn't think to get more batteries. I don't think I have a backup battery. Okay, so chapter 9, gases. Why are gases important? A couple reasons. They give us a neat little window in a lot of regards as to how molecules behave. Molecules, whether they're in a solid, liquid, or gas, if they are above 0 degrees Kelvin, are moving. In some cases, they're just vibrating in a solid, like this pen. We're at about 298 degrees Kelvin. Seems kind of hot, but we're only 25 degrees C. But the atoms in this pen, this marker, are vibrating. Where are they getting that energy? Their energy is directly proportional to their temperature in Kelvin. So they are vibrating. You cool it down, and they will still be vibrating, but less, not as energetically. Cool it down slower, and they get slower. Slower, lower, and they get slower, and they don't vibrate as far apart. This is why as you cool this thing down, it will actually get shorter. All right, a copper wire. You cool it down, and it gets shorter because the copper atoms are vibrating in there. You warm it up, they're vibrating a little bit more energetically. They're going further apart, coming back together further apart, and the wire gets longer. Cool it down, it gets shorter. So molecules, atoms are always moving. They have some kind of energy, and it's related to their temperature in Kelvin. So gases give us a little window into that. We can see molecules behaving in the gaseous state. They're not just vibrating, they're actually moving independently of one another. So the room is full of oxygen and nitrogen molecules. What are they doing? They're flying through the air until they hit something. So an oxygen molecule comes flying through here until it hits something. What's it going to hit? Well, if it hits nothing, it'll hit the ceiling. It may hit me. It may hit you. It may hit another oxygen molecule or a nitrogen molecule. And if it does, it bounces off of it. And that's what these molecules are doing. They're bouncing around in the room. So gases give us a little window into the behavior of atoms and molecules. Number 2, you just saw it in the problem we just solved. There are gases involved in chemical reactions. We started out with liquid nitroglycerin, and we ended up with 3 gases and water. So there are times when you have to deal with a gas as a reactant or a product, or both. Okay? So how would you do that? How do you deal with that? So we need to kind of learn the things that affect gases. Just quickly, either right here, you can see in blue are the elements that exist as gases at room temperature. They're in red on this periodic table. Those are gases at room temperature. Nitrogen, oxygen, helium, neon. Now, some of those are what we would call ideal gases. Their behavior will mimic these laws. The laws that I introduced to you will pretty accurately, or their behavior will pretty accurately follow that law. Ideal. What are some of them? Well, nitrogen is pretty ideal behavior. Oxygen, certainly helium, neon, argon are ideal gases. But fluorine and chlorine are not particularly ideal. They're not as ideal in behavior as these others. And some other gases like water. Okay, water is a liquid, but at, let's say, 150 degrees centigrade, water is a gas. It's boiled. It's above its boiling point, so it's a gas. But at 150 degrees C, water does not follow these laws very carefully. So it would be non-ideal. So water is an example of a non-ideal gas or a real gas. And towards the end of this chapter, and hopefully towards the end of today's time together, we'll get over to how to deal with a non-ideal gas. And that's a little bit more complicated problem. All right, so here are elements. Here are compounds that are gases: carbon monoxide, carbon dioxide, methane, ammonia. Sulfur dioxide is a gas. HF is a gas, and HCl is a gas. You can buy cylinders of anhydrous HCl, no water. Those cylinders will be dry, because if they're not dry, the HCl will dissolve in the water, produce hydrochloric acid, and start eating holes in the cylinder. So it has to be anhydrous. But you could buy a cylinder of HCl gas. If you bubble it into water, none of the bubbles will come out until you completely saturate that water, because the HCl will dissolve in the water and form hydrochloric acid. So you're familiar with hydrochloric acid, but HCl all by itself is actually gas. All right, physical characteristics of gases. They assume the volume and the shape of their containers. All right, the air in this room is expanded to every little nook and cranny of this room. It has filled the room completely. Let me see how my hot plate is doing over here. I got some steam going. Ooh, that's hot. That one's kind of out of water. What do I do about that? Nothing. All right. We'll get to that in a minute. Gases assume the volume and the shape of their containers, where a liquid, the liquid in this bottle, has a particular volume, but it has assumed the shape of the container. All right, it has no defined shape. It will assume the shape of any container you put it in. You pour that into a pan, it'll flow out into a pan. It won't change its volume. It'll have the same volume as it has in that bottle. Gases have much lower densities than liquids and solids. All right, now what we're going to be seeing is that gases are affected by 4 major variables. These 4 variables, if we can get a handle on these 4 things, we can say a lot about the gas. Pressure, volume, temperature, and this is going to be temperature in Kelvin and moles, the amount. So here we're talking about the amount of the gas. N is how much gas do you have there? Well, you know a little bit about moles. You know how to convert centigrade to Kelvin. You know that volume, we're talking about the amount of space something occupies. That's a half-liter bottle of drinking water. Half-liter, that's a volume. All right, but let's talk about pressure. That's a parameter we haven't talked a lot about. How do we measure pressure? What is pressure? Where does it come from? Where does it come from is here on this slide. As we sit here right now, we are all under a certain amount of pressure. We're sitting under 20-mile-high column of air, which is our atmosphere. All right? And you think, well, boy, this seems pretty light. You know, I don't feel anything. Actually, if you move your hand far enough, you do feel something. You feel the air blowing past your arm. So there is something in the room, and you can figure out what it is. You can fan yourself, and you can feel you're moving air around. But it is low density. My arm cuts through the air almost effortlessly. But there is air here. We are swimming around in it like a fish swims around in water. But the difference is the fish is swimming around in a much higher density substance, water. We're swimming around in a fluid that is very low density, but it is 20 miles high. And 20 miles high creates an atmosphere of pressure. 1 atmosphere. Okay, so years ago, and notice here, this is kind of showing you, if you look at this slide right here, altitude in miles. And remember, I said if you go out to 20 miles out here, the pressure drops off, not to zero, but the atmosphere is so thin, the pressure being exerted out 20 miles out there is so low that that's kind of a common distance out to say that's where the atmosphere stops. Doesn't really have an abrupt stop, but it's so thin that we're going to say we're at the end of it. If you get out above there, you're out of our atmosphere. But notice that, so 20 miles out. Let's go out 5 miles. So there's 1 atmosphere. 5 miles out, what do you have? You've got 5 miles. So you're 1/4 of the way to the top of the atmosphere, and you're at about a half of an atmosphere. So it doesn't go down linearly. It goes down asymptotically. All right? So that's about Mount Everest. So if you climb to the top of Mount Everest, you've climbed about 5 miles high, 29,000 feet, and you have half of the amount of air, half of the pressure of air that you would have at sea level. And then you go out to 10 miles, so you're halfway up to the top of the atmosphere, and look, you've already dropped 80% of the pressure. You're down to 0.2 atmospheres. And then at 20 miles out, you're down to less than 0.1, 95% of the, all right? You see that? It's not a linear thing. It's a asymptotic drop. How do I make this smaller again? There we go. All right, so Torricelli was a Italian investigator around 1643, invented the Torricelli barometer. And what he said, well, how could we measure atmospheric pressure? He used mercury, liquid mercury. Why? Because it's very high density, almost 14 times more dense than water. This is a vacuum in here. There's nothing in that tube. Nothing. How do you make that? Well, he would take the tube, fill it up with mercury, and then invert it into the pan of mercury, and the mercury in the tube would sag down to a certain level and stop right there. Why does it stop? Well, because the pressure, that's the pressure of the mercury. And what is this? This is the pressure of the atmosphere. So when those two pressures are equal, the atmosphere is pushing this way as hard as the mercury is pushing in the opposite way. It stops falling. You follow that? Does that seem reasonable, logical? That column of liquid is creating a certain amount of pressure, a force. It's pushing down with a certain force per unit area. But so is the 20 miles of air. pushing down with a force. And so 1 atmosphere, or the 20 miles of air column, is equal to 760 millimeter column of mercury. If we were to compare densities of the mercury, density of the air, we would find we're talking about the same weight of mercury to the same weight of air per unit area, force per unit area. So it ends up with this kind of odd comparison of atmospheric pressure to a certain column of mercury. Now this is 1 meter, 100 centimeters, 1,000 millimeters. So 10 centimeters is 100 millimeters, 200, 300, 400, 500, 600, 760, right there. So that Torricelli barometer had 1 atmosphere of pressure supports a column of mercury that high. And so this ends up being a neat little device to have in the lab or wherever, and you could, as the pressure goes down, the column of mercury will go down. As pressure goes up, the column of mercury will go up. That's why it has to be a vacuum in the top here, because it's never pushing against anything. It's just being pushed to a certain level because of the pressure of the atmosphere. Questions about that? It's how we measure pressure. In millimeters of mercury, and what you can see here is that 1 millimeter of mercury also equals 1 torr, and that's coming from Torricelli. So he has gotten a unit named after him, the torr. If we look at the atmosphere, the density of the atmosphere, you will also find this pressure equals force per unit area. You'll find that it is about 14.7 pounds per square inch. That is the amount of force that the atmosphere is exerting. 14.7 pounds per square inch, or you will see it as 14.7 psi, pounds per square inch. So automobile tires, they vary, but typically are inflated to about 32 pounds per square inch, 32 psi, which would be about 2 atmospheres. So you have 2 times atmospheric pressure inside your automobile tires. Now let's see, sometimes this works and sometimes this doesn't work. This is cold, but I don't know if it's cold enough. I wanted to have ice water in there. Got a hot can here. What have I got? I've got a hot can. I'm looking to see if there's some steam. Yeah, there's some steam coming out of that. There's steam coming out of that can. So let's try this. Back up. Put your goggles on. There you go. I've got ice water here. Now, be careful, or not be careful, but watch carefully. This won't take long if it works. I've got a can with boiling water inside of it. Get it boiling. I see a little bit of steam coming on, so that looks good. Let's see if this works. Nope. Let's try this one. I have some steam in it. I hear a little bit of water. Let's try another one. break, I'll pull up a little video, not of these cans, but of something even more dramatic than the can. What I was trying to demonstrate here is what would happen if we reduced the pressure inside the can and left the atmosphere around it. What would happen to that can? So at the break, I'll come back and show you that. I've got a little video that I'm pretty sure I could find and show you that. Which just demonstrates that the atmosphere does indeed generate a force. So really, you sitting right there, every square inch of your body has 14.7 pounds of atmospheric pressure pressing on it, every square inch of your body. So you thought exams put you under a lot of pressure? The atmosphere does it much more. All right? And just to relate this to the scuba diver, you know, scuba divers know as they go down deeper, their body is coming under greater pressure. And actually, about every 30 feet of water generates another atmosphere of pressure. So if Torricelli had made this barometer out of water, this tube would have had to have been 30 feet high. All right? He made it out of mercury because mercury has a density about 14 times greater than water, so it doesn't need to be 30 feet high. Only needs to be 1/15 of that, or about 2 feet high. 760 millimeters is 2.5 feet. All right, so 2.5 feet of mercury is generating the same amount of pressure as 30 feet of water. So a diver goes down to 30 feet, he's at 2 atmospheres of pressure on his body. 60 feet, 3 atmospheres. 90 feet, 4 atmospheres. The water pressure plus the air pressure above that. Okay, just quickly here, we have this, do this conversion. 1 atmosphere equals 760 millimeters of mercury. So convert 688 millimeters of mercury into atmospheres. Our dimensional analysis just tells us to put the millimeters of mercury down here, atmospheres up here. What do you get? 0.90. All right? Yeah, 688 millimeters of mercury pressure is less than an atmosphere, because a full atmosphere is 760. All right, be conversant with converting, because you're going to see at some times you are getting pressure in millimeters of mercury, and there's times when that has to be converted to atmospheres to go on. There's another example right there. Okay, this is just another slide showing Torricelli's barometer. Okay, let's get to our first law, Boyle's law. Boyle looked at pressure and volume. What he held constant was temperature and the amount of gas. So these are not variables, but pressure and volume are going to vary. Temperature is 25 degrees C. Berko, can you turn this light off? Thank you. Okay, so what Boyle did is started out with a certain amount of gas. He didn't even really need to know how much. He just needed to conduct the experiment in such a way that that amount of gas did not change. So he's got it in a cylinder here that isn't going to leak air in or out of this cylinder. So he starts out with 10 liters at 1 atmosphere, and he increases the pressure and asks the question, what's going to happen to the volume? He's not changing temperature. So just consider this as our condition, our initial condition, or condition 1. Condition 1. So what is P1 times V1? It is 1 atmosphere times 10 liters. It is 10 liter atmospheres. Then he moves on to condition 2. He makes a change. What does he change? Pressure. He doubles the pressure. What is P2 times V2? 2 atmospheres. And see, the volume decreased. The pressure doubled, the volume halved. It went down by a factor of 2. But look at it, it's still 10 liter atmospheres. It's constant. So Boyle said that pressure times volume is a constant if the amount of gas and the temperature are held steady. Then pressure times volume is going to be a constant value. So there is his law. Pressure times volume is a constant, or P1 times V1 equals P2 times V2. The volume of a gas is inversely proportional to the pressure if the temperature and number of moles are held constant. Sometimes you will see this written as Pi times Vi equals Pf times Vf. Same difference. The I standing for initial. My initial pressure times my initial volume is equal to my final pressure times my final volume. So those are just two different ways of writing the same law. You can see what a graph of it looks like. It's not a linear relationship. We've got pressure increasing here. And what's volume doing? It is decreasing. Pressure is increasing. Volume is decreasing. All right. Now, I'm going to quickly do a problem, and then I'm going to give you a problem to do, and then I think there's a third problem you can do after class, if you so desire. But I want to use this one to model how and this is not a difficult problem to solve, so bear with me as I kind of laboriously go through this, but I want to use it as a model of how you should approach these problems every step of the way, okay? Some of you already probably have done a lot of word problems, but if you haven't done a lot of word problems, let me suggest here's the way to approach them. Read them. Number 1, read the problem. Calculate the initial pressure of a gas that expanded from 1 liter to 7.5 liters and a final pressure of 5 atmospheres. Okay, now I'm telling you this is a Boyle's Law problem. I won't always do that. Now, on an exam, you may have a problem, and it doesn't say it's a Boyle's Law problem. You have to figure that out. Initial pressure, P1. Calculate. Oh, that's what they want me to figure out. this is the other thing I do. I go back through the problem and I identify what is the information I'm being given, and I identify what I'm being asked to calculate. The gas expanded from, so that's V1. 2, so it went from initially 1 liter to finally 7.5 liters. So that's V1 and V2. And a final pressure, that's P2. So I've been told it's a Boyle's Law problem. So I need the Boyle's Law equation. The Boyle's Law equation has 4 parameters associated with it. If I know 3 of them, I can calculate the 4th one. I know 3 of them. Okay, next step. I take my law. I'm being asked to calculate P1. So I want to convert this into that expression. P1 equals what? Well, if I divide both sides of this equation by V1, I get that P1 equals P2 V2 divided by V1. All right, I'd like to get to that point before I start fiddling around with numbers. Now I plug the numbers into this equation. All right, I haven't touched my calculator. Don't touch your calculator until I touch mine. All right? Don't rush, because you have the tendency of wanting to get a number. I don't want you to get a number. I want you to get an answer. Correct answer to this problem. So don't rush into a numerical calculation until you know you're doing the right calculation. V2 is 7.5 liters. V1 is 1 liter. Dimensional analysis. Next step. Cross out the liters. I've got atmospheres. Atmospheres is the unit. Is that a pressure unit? Yes. Okay? All right? I know I've taxed your patience going through it so slowly. But the other problems are going to get more complicated. And so if you kind of go through this, Boyle's Law is the easiest problems to solve. You go through it like this. Now pick up your calculator. And you have a numerical calculation to do to get a number, but you're going to get a number with the right unit. You're going to know you set the problem up correctly. And what's the answer? All right, 37.5 atmospheres. All right? So initially this was really high pressure, low volume. The pressure decreased to 5 atmospheres. It decreased by a factor of 7.5. The volume increased by a factor of 7.5. Okay, now go ahead and use that method and solve this next problem. Boyle's Law problem. Okay, let's do this and then maybe take a break. Okay, if 1 liter of a gas at 5 atmospheres is compressed to 0.2 liters, what would the pressure of this gas be? 1 liter is what? What parameter? V1 of a gas at 5 atmospheres is what parameter? Is compressed to, what is that? Point. No, this is V2. What would the pressure, right? P2. Okay? So run through that. You want to calculate P2. So divide both sides by V2. And you end up with that expression, and you punch the numbers in, and you get what answer? 25. Atmospheres. Okay? So that's Boyle's law. Let's see. Okay, we're skipping the Coke can. I don't know if we'll have sound on here or not. You can Google this later as well. Railcar implosion. This is a little training session. They've got a bunch of railmen standing along the side here watching this. They're basically, I'm sure their supervisors or whoever's conducting this training is saying, okay, this is what you don't want to do. This is what you don't want to do. Now this is just 18 seconds long, it looks like. And I don't know if we'll have sound or not, but just watch what happens. Oh, what happened? I didn't hit the right button.
760. Gewonnen hat Jakob Dich.
Okay. What's happening there? I mean, this can happen in a railway station. You're unloading, let's say, a rail car of gasoline or any liquid. You're pumping out the rail car. And if you have all the valves closed on that rail car, you're pumping the liquid out of the car and nothing is replacing it. You're creating a vacuum in the car as you empty the rail car. And I just told you there's 14.7 pounds per square inch of atmospheric pressure on us, on everything, on this building, everything. So if you evacuate a space, all of a sudden there's nothing pushing back. And so if you were to take the surface area of that rail car, it has tons of pressure on it, tons of force on it, and it will implode the rail car and possibly kill someone standing next to it. Because, I mean, it happens, bam, like that. That rail car gets to the point where its mechanical strength cannot withstand the atmospheric pressure on it, and it crushes the rail car. That's what I was trying to reproduce here, and I have done it on occasion by boiling the water in the can and then turning it over, because at that point in time the can is full of steam. And if I dip it over into ice water, the can cools down, condenses the steam, and creates a vacuum, creates a sudden vacuum inside the can, and it'll crush the can. Okay. Do you need a break, or should we do one more law, and then when we get to doing a calculation, I'll give you a break? All right? Is that a deal? All right, so let's go on to Charles' law. Let me get back to this screen, hopefully. Charles Boyle's law. So just keep in mind there's other problems in here. There's slides with problems on them. Oh, I said that we would. Well, Boyle's is the easiest one. So let's do a Charles law, and then I'll find a Charles law problem, and I'll say let's do that. Have a break. We'll come back and make sure we got the right answer. Charles looked at volume and temperature. And you notice here that pressure is always at 1 atmosphere in this experiment, this Charles law demonstration or experiment. Pressure and again the amount of gas are held constant. So each of these men, Boyle and now Charles, looked at 2 variables holding other things unchanged. So it's a methodical experiment here. Started out with a certain amount of gas, and he doesn't change that. He doesn't add or let any gas escape, but he does change the temperature. He's increasing temperature from 273 to 546. This is condition 1. This is condition 2. So this is your volume 1, and this is your T1. This is your volume 2. This is your T2. V1 over T1 is 1 over 273. V2 over T2 is 2 over 546. What has he done in Kelvin? He's actually doubled the temperature. Okay, he's doubled the temperature from 273 to 546. So if I divide that by 2 and that by 2, I get 1 over 273. So that remains constant. So Charles' law is that volume over temperature is a constant. A new constant, but a constant. Won't change. So V1 over T1 equals V2 over T2. You increase temperature, you increase volume. They vary directly with one another. You increase one, it increases the other one. That's a direct relationship, or directly proportional. Volume of a gas varies directly with the absolute temperature if the pressure and number of moles of gas are held constant. And you can see here, you do get a linear relationship. Temperature is increasing. What's happening to volume? It's increasing. They're directly proportional to each other. So you get a nice linear relationship. And actually you can do these kinds of experiments and get really pretty good data. If with an ideal gas, with a gas that behaves ideally like helium or neon, you can see, boy, I doubled the temperature, it doubled the volume. I quadrupled the temperature, it quadrupled the volume. It's direct proportionality. All right, now this problem let me do this problem, and this will prove an important point that will be helpful to you throughout the gas law problems you solve. All right, a gas at that temperature, T1, and this volume, V1, is heated to, that's T2. What is the volume at this higher temperature? V2 is your unknown. All right, Charles' law says that V1 over T1 equals V2 over T2. V2 is my unknown, so I want an expression like this. V2 all by itself. Multiply both sides of this equation by T2. T2 crosses out, and I get that V1 times T2 divided by T1, V2 equals that. Okay, now, make sure you get the right things in the right place. This is your unknown. What am I going to do with this 25 degrees centigrade? Change it to Kelvin. And the 100 degrees centigrade. Change it. The initial volume was 3 liters. So I've got 3 liters times 373 Kelvin divided by 298 Kelvin equals what? Well, Kelvin crosses out. Let's be as methodical as I said we should be. Dimensional analysis, the volume is coming out in liters. We're happy with that. So what is the new volume going to be?
3476.
Okay? Okay, we'll before we pick out another problem, let me just say this. Let's pretend there's a skeptic in this audience that says, why did we go to all this trouble, convert to Kelvin, and why does it even matter? So let's do this problem, and let's keep centigrade. So the final temperature is 100 degrees centigrade. The initial temperature was 25 degrees centigrade. Centigrade crosses out. Still gets me to liters. Everything looks hunky-dory, dimensional analysis-wise. But what's the answer now? 12 liters. Why? In centigrade, it appears that you quadrupled the temperature. You didn't do that. You just raised it a little bit. You started at 298 Kelvin. You raised it to 373 Kelvin. That was a incremental. You didn't even double the temperature. That's not even doubling the temperature. And it looks like you quadrupled it. So by quadrupling it, you come up with this wrong answer. Okay, so in gas law problems, always convert to Kelvin. And let me just make a point about that. Why does it, even Charles Law says that the volume varies directly with the absolute temperature. It spells it out in there. It doesn't just vary directly with temperature. It varies directly with Kelvin. This is Kelvin. And why is that? Because centigrade, its reference points are the boiling point of water and the freezing point of water. That is how a centigrade temperature thermometer is constructed. What is this? The absolute temperature? Kelvin? I'm sorry. Kelvin, 0 Kelvin equals 0 energy. It is the only temperature scale that's directly proportional to energy. And why is the volume varying directly with Kelvin temperature? Because as you raise the temperature, you're raising the energy, you're making these molecules move more, and they will expand a balloon, or they'll expand in a chamber, because they are moving faster. They've got more energy. They're bouncing against the walls of that cylinder with greater force that's directly proportional to their energy, which is directly proportional to their Kelvin temperature. Okay, so that's why Kelvin dictates this. Now let me find a Charles law problem. Well, problem 13. Problem 13, which one do we want to do here? Allowed to expand it. Oh, that's constant temperature. 17. 36.4 liters of methane is heated from 25 to 88 at constant pressure. Okay, there you go. 17. Go ahead and do problem 17. Take a break. Work on that. Take a little break. In about 25 after, let's come back and do 17. Let me just mention, because some students like this, here's Boyle's law. Excuse me. This is Charles' law. Charles' law. Now you can convert this into, you can cross multiply, just cross multiply these and get that V1 times T2 equals V2 times T1. And now you have a representation of Charles' law that looks a lot like Boyle's law. It's not pressure and volume, it's volume and temperature, but it is, you don't have any parameter that's in the denominator. And let's just look at that. So this is also Charles' law.
Does that mean that when temperature increases, volume also increases that? They're not inversely?
No, because see, we haven't changed anything. We've got the second temperature aligned with the first volume.
I know, but I'm saying if the volume were to increase, the temperature would increase as well, right?
Yes.
As well.
Yeah.
Versus Boyle's, it's the opposite.
Right. Boyle's, as pressure increases, volume decreases. Right. It's the opposite. Right. So here, if I want to solve for V2, what am I going to do? I'm going to just divide both sides by T1, and that gets me to V2 equals V1 times T2 divided by T1. Gets me to the same expression. Whether I use Charles' law in its original form or convert it into V1 T2 equals V2 T1. And work with it either way you'd like. All right, back to the slides. Charles' law. I think we've covered Charles' law. There's another problem right there. And another problem right there. Charles' law. Avogadro's law, I'm not going to do a bunch of problems, but let's just mention it. Oh, I know what we've missed here. Where's combined gas law? Here we go. Combined gas law. Before we go on to Avogadro's law, the combined gas law is just Boyle's plus Charles. that is what we're combining. Boyle's law says that pressure times volume is a constant. Charles says volume divided by temperature is a constant. So pressure times volume divided by temperature is a constant. That's the combined gas law. And I won't do a whole lot of, well, there are ideal gas law problems in here. I'll tell you what, if we have time at the end of the period, we'll come back and try to do like question 19. That's a combined gas law. Or what we'll do at the end is we'll pull some of this up and I'll just say, okay, what law is this? What law do you need to solve for question 13, 14, 15, 16? We won't necessarily solve them all, but we'll at least identify some of the laws if we have time, and we might have time. Yeah, we've got an hour. We've got another hour and 10 minutes. So we should get there. So we'll maybe come back and do a combined gas law problem, but there is a combined gas law. Or if we cross-multiplied in here, we would end up with P1 V1 times T2 equals P2 times V2 times T1. If we wanted to get the temperatures out of the denominator, we could do that by cross-multiplying and end up with that expression, which is also the combined gas law, just expressed a little different terms. But combined gas law problems you need to be given 5 of these 6 parameters to solve a combined gas law problem. All right, like I said, we may revisit this a little bit later. Let's move on so that we get to the real pay dirt here. The real gold that we want to get to here is ideal gas law. That's why I wore this shirt today, by the way. This is the ideal gas law. I'll tell you a little bit about this shirt later. So Avogadro said, I am going to look at the relationship between volume and the number of moles of the gas. So what is he holding constant? Temperature and pressure. So he's not varying pressure, he's not varying temperature. Oh, I meant to go get another balloon. Do I have another balloon? I got one. Avogadro's law. It's as simple as this. It's as simple as blowing up a balloon. Here's a balloon. There's nothing in it. All right? It's empty. I fill my lungs with air. I blow the contents of my lungs into the balloon, and we got a volume. That's V1. And what's N1? Well, the number of moles of air that I blew in there. Let's do that again. I'm going to add more air to the balloon. What happened to the volume? It increases. So as I increase the moles of gas, volume increases. All right? Avogadro's law. So the initial volume divided by the initial amount of the initial moles of gas is a constant. Or, yeah, as you increase the amount of gas, you increase the volume. If we had a picture here of a cylinder, with a piston on it, we would actually have a little valve over here where we could pump in more gas. And we would start out, pressure is going to stay constant, We're going to start out an initial volume, initial volume here with an initial amount of gas. We're going to put in 2 times that amount of gas, and we're going to get 2 times the initial volume. You double the moles, you double the volume. All right, so now this is the granddaddy of them all in terms of combining the gas laws. We don't call it the combined gas law, we call it the ideal gas law. But what are we doing? We're taking Boyle's law, pressure times volume is a constant, temperature and the moles of gas are not changing. Charles' law, volume divided by temperature is a constant, pressure and the amount of gas are held constant. Avogadro's law, volume divided by the moles is a constant. And so we're bringing all of that together here. Let's write that a little bit bigger over here. So we have pressure times volume divided by the number of moles times temperature is a constant. And now we're going to define that constant. This is going to be the ideal gas law constant. Right there. We're not just going to call it K. We're going to give it a number, 0.0821 liter atmospheres per mole degree Kelvin. That's a mouthful, but that's the ideal gas law constant. And I like to write this on the board. Some people say, boy, do we have to memorize all these? I don't know. It's not hard. You'd like me to answer that question, wouldn't you? Well, let me just say this. Here's where we are. All right, there's our ideal gas law constant. What law is that? Boyle's. What law is that? What law is that? Combined. And what law is that? Avogadro's. They're all right there, staring you in the face. All right? So what do we do here? We multiply this by NT. And so we multiply this by NT. And what do we get? PV equals NRT. That's the ideal gas law. It takes all of these parameters that affect the gas. These are the 4 variables that affect gases. What pressure is it under? What volume is it in? What is its temperature? How many moles of the gas are there? You know 3 of those 4 things, and you can calculate the 4th one using the ideal gas law. That's the beauty of this law. Notice that I don't have P1, V1 equals N1, T1. I don't have that in there. I don't need to compare my initial condition to my second condition. I can say right now, right here, say I had a cylinder of gas. Certain pressure on it here. And I know the volume of this cylinder. I know the temperature that cylinder, let's say it's sitting at room temperature, 298 Kelvin. I know the pressure, check, well, I got a pressure gauge on it, so I read the pressure, whatever it is, 1,500 pounds per square inch. I convert that into atmospheres. And I want to know how many moles of that gas are in that cylinder. I could calculate it by just knowing the volume of the cylinder, the temperature of the cylinder, the pressure of the cylinder. I can tell you how much gas is in the cylinder, because it's going to behave according to this equation. Talking about an ideal gas. All right, so remember that law. Remember that law. And then just, you say, well, how do I remember all the other laws? Well, just convert it back into this form. Convert it back into that form of the constant over here and all of these variables right there, and you have all the laws looking at you. All right? So whether I give them to you on the exam or not, and probably before the exam I should tell you. I think that's why you laughed. You'd really like to know that. Yeah, I'll probably give them to you. But you can know them right here. And how about R? Do you have to memorize R? Anybody know? No? Why not? It's on a periodic table. It's on the back of your periodic table. Ideal gas law constant with its units. All right, so you get into an exam and you go, oh, what's R? It's there right there. A little bit about the shirt. About 5 years ago, a woman that works with my wife, her sister and brother-in-law were visiting here from, I think, Portland, Oregon. And we went to Rudy's for dinner. And so I met this guy for the first time. What do you do? You know, we're talking, oh, I teach Northwest Vista College. Oh, what do you teach? Chemistry. Chemistry. He goes, oh, PV equals nRT. He spouts this off. He wasn't a chemist. He said, that's the only thing I remember from high school chemistry. It's PV equals nRT. So do you see how memorable this is? So where did this come from? 2 months later or so, brown envelope appears in our mailbox, and I take it in and open it up, and he sent me this shirt. He had this shirt made and sent it to me. So semester after semester, I get to this chapter, I wear this shirt. PV equals nRT. Sometimes I wear it for the exam. All right, so let's do a couple. What do you, there is another unit here, but don't worry too much about that. What that's telling you right there is there is a relationship between joules and liter atmospheres. Liter atmospheres is a energy term. Liter atmospheres and joules go together. So this is the one you got to really work with. But the units on the R are telling you what these units need to be for every one of these other parameters. N needs to be moles. Temperature needs to be Kelvin. All right? So before you can plug numbers in, data, whatever it is you're given, you got to make sure you have it in those units, because this constant is in those units. Not going to work with milliliters. It's not going to work with degrees centigrade. Or it's not going to work with grams of gas. Not grams, it's moles. Okay, so let's do 1 or 2 problems. Calculate them. Should we do these, or should we just do them on our thing here? You want to do them in here?
Yeah.
Okay, you'd rather do them in here. All right, number 10. Let's see if I can pull that up again right here. Where did that go? Oh, it's right here. Number 10. Oh, how did I do that? Look at what I just did. I won't ever be able to do that again, because I don't know how I did it. I don't know. Number 10. Calculate the number of moles of a gas that is present in a 4.55 liter cylinder at 35 degrees centigrade if the gas exerts a pressure of 0.9 atmospheres. So there's a pressure, there's a temperature, there's a volume, calculate the moles. N is unknown. All right, so I look at this. So what gas law is going to solve this problem? The ideal gas law. How did I come to that conclusion? Well, I've got a pressure. I've got a pressure, got a volume. I'm being asked to calculate moles. I always have R, and I'm being given a temperature. So I'm being given 3 of those 4 variables and asked to calculate the 4th one. The only law that can attack this is the ideal gas law. All right, so I isolate N. So the number of moles is going to equal the pressure times the volume divided by RT. T equals 35 plus 273. So what is that? 308 Kelvin. So we got 308 Kelvin. We have pressure in atmospheres. That's good. We've got volume in liters. That's good. We've converted our temperature to Kelvin, and we are being asked moles, which is what the ideal gas law can calculate. So I got 0.900 atmospheres. Let's do the dimensional analysis on this. Volume is 4.55 liters. I've got 0.0821 liter atmospheres per mole Kelvin. And down here in the bottom I have 308 Kelvin. So liters cross out with liters. Atmospheres in the numerator, atmospheres in the denominator. I look down in the denominator and I have Kelvin, and I have Kelvin in a fraction in the denominator. So that Kelvin crosses out with that Kelvin. And really what I've got here now is 1 over moles. Because that's what I got left in the way of units. Everything else, an atmosphere divided by an atmosphere is 1. A liter divided by a liter is 1. So I just have 1 divided by 1 over moles, which is the same as 1 times moles over 1 moles. It even works out, even with this constant. And the units on the constant. So, now pick up your calculator. How many moles of gas? Can you see over top of this? How many moles? Yeah, all right. So you're going off of 2 significant figures there. But if we take that and add 273 to it, we do get, so 273 plus 35, it allows us to have 3 significant figures. 0.162 moles. That's how many moles of gas are in that cylinder. Notice that it doesn't say what gas. That's kind of curious. We'll come back to that. Right now that we're at 11, what law would 11 be solved by? Oh, let's do 11. Let's do 11 because 11 proves another point. All right, be able to handle a problem like 11. Let's see, that reminds me of the Sound of Music. What are you going to do with a problem like Maria? Anybody know the Sound of Music? What are we going to do with a problem like this? It has grams, doesn't have moles. All right, so you see pressure here. You see temperature here. Calculate the volume. That's your unknown, but you don't see moles. But what do you see? Grams. You have an amount of gas, but it's in grams. So this is going to be an ideal gas law problem, but it's going to be a two-step problem. First calculate the moles of neon, and then convert the moles of neon to grams. Oh, no, I'm sorry. Sorry. Back up. Forget it. Wait, first. I'm sorry. I was thinking they were asking for grams. They're asking for volume. So first, convert your grams of neon to moles. Then you're going to have moles, pressure, temperature, and you'll be able to calculate volume. You with me? So just take your 27.5 grams of neon. I don't know why I'm doing this. I hope there's another one like this you have to do yourselves. You got 1 mole is 20.18 grams of neon. 1/8, yeah. So how many moles is that? What problem are we on? 11? Touch screens. So what is that answer again? I'm sorry. 1.36 moles of neon. Okay. So now we have PV equals nRT, and we want to solve for V. So volume is going to equal nRT over P, and we just calculated N. Temperature is 300, is that right? 300 Kelvin. And pressure is 0.455 atmospheres. So the pressure is in atmospheres. The amount of gas now is in moles. The temperature is in Kelvin. And we get the volume. Something like 33.5. And what are the units? We didn't do the dimensional analysis, but volume is going to be in what? You got what?
73.6.
What did I do? Did I do something wrong here? 1.36 times. Oh, okay. I think I divided by 4 times 300 divided by 0.455. Okay. I didn't divide by the pressure. Okay. Thank you. $73.6. And what's the units? Liters. 73.6 liters. All right. So let's come out of here for a minute. Go back into our slides. Just be aware that you got a lot of slides in here with nothing but problems on them. Not a lot, but 5 or 6, 7 more that you could go in and do. And they're like under here, it's talking about ideal gas law. So it goes into a bunch of ideal gas law problems where you're either given the moles of the gas or you're given the grams of a gas, or you might be, okay, here's a problem. We won't do it right now, but here's a slide in there. What is it saying? It's asking to calculate how many grams of CO2 are present in this cylinder. You got a volume, you got a temperature, you've got a pressure. So this problem, what you need to do is first calculate the moles of CO2 that are in this cylinder. You can do that. You can solve for N. And then second, convert your moles of CO2 into grams of CO2. You can do that. You know how to go from moles to grams using the molar mass, okay? So there's different permutations, different kinds of things that come into play. That's one of the slides. This looks like the same problem, but it's giving you the pressure in millimeters of mercury, so you need to convert this into atmospheres before you can plug that number into the ideal gas law. Just like you need to convert centigrade into Kelvin. All right. Next, how are we doing? You've got this thing to kind of keep track of where we are. We've got Boyle, Charles, combined, Avogadro, ideal. Now we want to mention what STP is. You know what R is now? It's the ideal gas law constant. You're putting equations here, just kind of a neat little, score sheet. What are these things? What is STP? Standard temperature and pressure. So you can see that temperature and pressure affects a gas. You'd say, well, I've got 20 liters of this gas over here, and I've got 10 liters of this gas over here. Well, the first thing I'm going to ask you, well, are they at the same temperature and pressure? Because I could change the temperature and pressure, and I can have 20 liters of each one of them. So standard temperature and pressure ends up being a reference point where we could compare one gas to another gas. And we just say, well, let's just talk about them at the same temperature and pressure. So standard pressure is the freezing point of water, 273 degrees Kelvin. Standard pressure is more or less sea level, one complete atmosphere. One atmosphere, pressure. Those are your standard temperature and pressure. Okay, now, All right, now you know what that is, all right? Let's use that. And I really want to prove a point over here. So what I want you to do on this problem, I want you to use R to 4 significant figures, and that's going to be 0.082. Instead of 1, it's 0.08206 liter atmospheres per mole Kelvin. For this calculation, use the ideal gas law to calculate the volume of 1 mole, and we're talking about exactly 1 mole of a gas at standard temperature and pressure. So this is what you want to calculate. You've given 1 mole. You now know what the standard temperature is and standard pressure is. So it seems like a problem that doesn't have enough information, but by saying STP, it's giving you temperature and pressure. And I've asked you for 1 mole of the gas. So do this calculation and use this R, and you'll see why in a minute. But I want to do this one very accurately, as accurately as we can do it, or a little bit more accurately, to 4 significant figures. Okay. What do you get when you do the math? Yeah, there you go. 22, I'm going to write this really big. 22.4 liters. Let's put a big V in there. Okay, this is not just a problem. This is an important little problem that I want to dwell on here for a minute. What gas are we talking about? What gas? Did it say what gas? Didn't say what gas. Actually, it's any ideal gas. Any ideal gas. So we could be talking about hydrogen, oxygen, nitrogen, helium, argon, neon. 1 mole of each one of those gases at standard temperature and pressure, 273 degrees Kelvin, 1 atmosphere pressure, will occupy that volume, 22.4 liters. That you know, I want that to kind of sink in. Let me make that even more difficult for you to believe. This weighs 2.02 grams per mole. Now we're talking about 1 mole of each of these gases. This one weighs 32. Oxygen weighs 32 grams per mole. Nitrogen, 28 grams per mole. Argon is 39.9 grams per mole. Helium, tiny little one, 4 grams. And neon, 20. They weigh different, different weights. But they will occupy, that's a mole. That's 6.022 times 10 to the 23rd. That's the thing that's common here. We're talking about the same number of particles, whether that particle is an atom or that is a molecule. 32 grams of oxygen is Avogadro's number of oxygen molecules. 4 grams of helium is Avogadro's number of helium atoms. So that 22.4, and to give you an idea of that size, it's about a basketball. A basketball is a little less than 22.4 liters of volume. So that's about the volume we're talking about. That amount of any ideal gas is roughly a mole of that ideal gas. So bouncing around inside that volume is the same number of particles. All right, but what's going on here? I mentioned a little while ago that that the Kelvin temperature in Kelvin is proportional to energy. So at standard temperature, 273 degrees centigrade, 273 degrees Kelvin, all of those gases would have the same amount of kinetic energy. They have the same amount of kinetic energy. And you can, I want an E there. So the kinetic energy is equal to 1/2 times the mass times the velocity squared. So the temperature in Kelvin is directly proportional to energy. The energy is 1/2 the mass of the particle times the square of its velocity. So if the energy of the hydrogen, it's got the same energy as the argon, and the hydrogen is lighter, the argon is heavy, so the mass of the hydrogen is low. What does that mean about its velocity? The mass of the hydrogen times the velocity of the hydrogen squared is going to equal 1/2 the mass of the argon times the velocity of the argon. V here is not volume, it's velocity.
Velocity must be fast.
On what? Which one? Hydrogen. Hydrogen weighs less, it's moving faster. The argon is heavier, 30, almost 40 grams, so it's almost 20 times heavier than the hydrogen. It's moving a lot slower. So what does create pressure? What's holding that balloon? What's holding that balloon in that volume right there? I blew the air in the balloon. What's happening? The air is bouncing off the inside of the balloon with a certain amount of force. The oxygen and nitrogen atom molecules are hitting the insides of the walls of the balloon with a certain amount of force that's proportional to the temperature that they are at. Their temperature is dictating their velocity. All right, so things are moving faster. Does it hurt more if you get hit by a BMW going 100 miles an hour versus 20 miles an hour? Hurts a lot more. You got a lot more force. Momentum is mass times velocity. That's your momentum. So the hydrogens are tiny, but they're moving really fast. The argons are big, heavier, and they're moving slower. But when they hit the inside of the balloon, they hit with equal momentum or force. That's what's going on here. So this number, 22.4, is one I want you to remember. That's this molar volume of an ideal gas at standard temperature and pressure. It's 22.4 liters. That's the molar volume. Now that's just not at any temperature and pressure. That has to be at standard temperature and pressure. You move off of standard temperature or move off of standard pressure, then you have to calculate this number. You can't just say, oh, a mole of a gas is always that volume. Only at standard temperature and pressure. But as we compare these ideal gases to one another, that's what we come up with. Well, there you go. There it is visually. All right. The 22.4 liters, a little bit bigger than, quite a bit bigger than a basketball, but it's giving you an idea of what that is. And they get it to 22.414 liters, a little bit more accurately. Okay? So, all right. You guys need a break? I need a break.
So for number 20, it gives you like a condition that says calculate the volume at STP. So condition wouldn't even matter. Just volume is 22.4.
Okay. Calculate its volume. No, that's not an ideal gas law problem.
So
That's a combined gas law problem. Because what do you got? You got a pressure, a temperature, and a volume. And then it says at STP, it's giving you a new temperature, a new pressure, and asking you for the new volume. So that is number 20 is a combined gas law problem, if you want to make note of that. And like I said, if we have time, which I don't know if we will, I got two more meaty this next one right here, stoichiometry with gases, and then how do we handle a non-ideal gas. So we've got two more meaty calculations to get into. So take a quick break, 3-4 minutes, and we'll do that. And I put them both due. I said we're trying to get on a trajectory here of an exam next Tuesday. Could we possibly do that? Do we have to do? We got chapter 4. We're doing chapter 5 or 9, and then we got to go back and do chapter 5. So yeah, we're finishing 9 today. We're going to do chapter 5 Thursday, so it is possible. So, but that would mean I need to get quiz number 5 in there too. All right, so they're both due at midnight on Monday. But don't leave them for midnight on Monday. I mean, you just turned in this packet. I'll try to get this chapter 4 packet back to you on Thursday. So if you want to have that in your hands when you do that, we'll have to figure out what to do about chapter 5 or 9 packet. All right, so Thursday, Friday-ish, you should jump in and do this. You might have to jump in and do chapter 9. Okay, I'll have to think about this. How do we do all this? Because you got this packet, and you may be able to, you should be able to finish this packet. If we do another problem or two, you may be able to finish this packet for Thursday. Yes?
Do you have actually packets? Will you also put the solutions on your website?
And when I have them, and actually, yeah, this one I've got this. Do I have all the solutions?
Or just run that for us?
Yeah, I've got this one pretty well solved. I'm not sure I have every question, but I know I have some of them. Yeah, okay. All right. Okay, so pay attention to this, and I'll try to get some other, get the other quiz up there too. All right, so there's 2 more important things to look at. I mentioned as we started chapter 9 here that one reason why we need to understand how gases behave is that they show up in chemical equations, chemical reactions. And this is just showing you, just kind of a diagram how you would handle an equation with a gas in it. When a chemical reaction produces a gas, you can't readily kind of collect it and go in and put it on a scale and weigh it. It's a gas. You collect it. It's at a certain pressure. It is occupying a certain volume. It's at a certain temperature. But you can use those numbers to figure out how many moles of the gas you have. How many moles of gas did you produce? So let's take an example. Let's take a relatively straightforward example here. Here is a decomposition. This isn't nitroglycerin, but we got potassium chlorate. It's decomposing into potassium chloride and oxygen, which is a gas. This is a solid. This is a solid. So we've got a solid decomposing into a solid and a gas. If the decomposition of potassium chlorate results in 3.25 liters of oxygen being collected at STP, calculate the grams of KClO3 initially that decomposed. Well, that's curious. You know how to go from the grams of oxygen back to moles of oxygen to moles of KClO3 to grams. You know how to do that. But the problem doesn't tell you how many grams of oxygen. It gives you a pressure, standard pressure, gives you a temperature, standard temperature. It gives you a volume of oxygen, 3.25 liters of oxygen. And what could you do with those numbers? What can you calculate now?
Figure out the moles and go to grams.
You can figure out the moles, N, and you won't have to go to grams. If you know N, you can jump right over here to moles of KClO3 to grams of KClO3. You don't even ever have to figure out how many grams of oxygen. You could. You could figure out how many grams of oxygen, but you don't have to. Because the ideal gas law is going to give you moles of oxygen. Okay, so let's do this. So the very first thing we need to calculate is how many moles of oxygen is this. PV equals nRT. So N equals PV over RT. 1. Volume is 3.25. Please forgive me. I'm not going to put the units down right now, but we could. R is 0.0821, and T is 273. Now remember, the moles of oxygen equals this N. That's what N is. N is the moles of oxygen. How many moles of oxygen? Point 145 moles of oxygen. All right. So, okay, we don't need to go to grams. We've got moles of oxygen. So we got 0.145 moles of oxygen. Now we bring in our coefficients. You get 2 moles of KClO3 for every 3 moles of oxygen. And then the molar mass of KClO3, I think I almost know this by heart. Is it like 122? 1 what?
106.50.
Is it? Okay. Why am I remembering 122? I don't know. So K is 39.9.
Wait, no, I forgot. You're right. I missed an oxygen, but O2.
Okay, it's O3. So it's 122 point what? 55 grams of KClO3 per 1 mole KClO3. All right? All right, so see, you didn't need to figure out the grams of oxygen because the ideal gas law was taking us right to moles of oxygen. And you can relate moles of oxygen to moles of KClO3 to grams of KClO3. So what do we get, about 11.8? 11.8 grams of KClO3. All right, so definitely expect on the quiz, on the exam, I mean on the final exam, a stoichiometry problem that requires you to apply the ideal gas law to the situation. And here's an example. right here. And I don't know if we have time, but which one did I say? Did I say there was one like that here? A stoichiometry problem.
Still Dalton's law of partial pressure.
Yeah, we haven't done Dalton's law of partial pressures yet. I think, let's see, I think 23, is that a stoichiometry problem? 9 liters of NO are reacted with excess oxygen, STP. What is the volume in liters? Yeah, that's a fairly simple one actually, number 23.
26?
26 is definitely, you want to do 26?
Yeah.
Go ahead and do 26. The one that we have to get to is 27, A and B. But go ahead, dive into 26. Now that you see how I did that, try to do 26. And everybody calculate it, all right? This is the time to learn this. Have your calculators and be working these problems out. This is a valuable time to learn these. Oh, okay, this also uses Dalton's law of partial pressures. Number 26 does. Let me tell you how you got to do that. Okay, 26 has a little wrinkle in it. Dalton's law of partial pressures. What's going on there? Okay, let me. This is an ideal gas law problem with stoichiometry, but it's saying here we've collected the hydrogen has been collected over water at 25 degrees C. Now let me just draw on the board what this looks like in the laboratory. What this looks like is this. Now what are we reacting? So okay, so we have a reaction going on here. Let's see, we've got some water here, and we want to collect this gas. So we have a little flask here like this, and it's got a side arm on it like this, and we put a rubber stopper in here, and we put a tube like this, and what do? We run this tube up into a bottle. So we get a bottle here, some sort of a container, and it's full of water. So we fill it up with water, put a piece of glass over top of it, put it down in this water so that there's no gas in it. And we put this tube in here. Now what are we reacting? We're reacting sodium with water. So we take our sodium metal, chunk of metal, it's too big to get in there. So here's our sodium metal, take the stopper off of there, and we throw the sodium in there, put the stopper back on. And what happens? Sodium reacts with the water, it forms sodium hydroxide in here, and hydrogen gas starts bubbling out in here. Comes in here, and it starts accumulating in here. So we end up with this volume of hydrogen gas. That's what we mean by collecting it over water. started out with a bottle and nothing but water in it. Now it's got hydrogen in it, but what else does it have in there? What other gas is in there with the hydrogen? No oxygen. We completely got all the air out of that bottle. Well, there might have been a little bit of it here from the air that was in here. That's true. But what other gas is in there? Does water have a vapor pressure? This gas in here is totally saturated with water vapor. Why? Because it bubbled right through the water. And so there is a vapor pressure of water at the temperature at which this gas is being collected. And you can pick up your phone and type in there vapor pressure of water, and you'll first hit you get will be, as a function of temperature, what's the vapor pressure of water? And this is at 25 degrees C, and it's saying the vapor pressure of water at 25 degrees C is 0.0313 atmospheres. Usually they will give that number in torr or millimeters of mercury. Vapor pressure of water. So what do we have to do with that? We have to just make a slight compensation. And we use Dalton's law of partial pressures. Dalton's law says this, that the total pressure of a mixture of gases is equal to the sum of the individual pressures of those gases. So what you have in here is you're going to have the pressure of the hydrogen plus the pressure, the vapor pressure of the water. So the vapor pressure of the water is going to equal 1 atmosphere. That's the total pressure. So what's the pressure of the hydrogen going to be? If we subtract the pressure of the water from here, then we have to take this and subtract the pressure of the water from here is the pressure of the hydrogen. So before we can do the ideal gas law, we have to compensate for the pressure of the water vapor that is in our collection flask. We know the volume of this gas, and it's generating 1 atmosphere pressure because that's what the pressure is that day. But it's hydrogen and water vapor mixed together. So if we subtract out the vapor pressure of the water, we get that the pressure of the hydrogen is what? There you go. All right?
So that's the pressure we use for the equation.
That is the pressure you use for the ideal gas law, because we want to calculate moles of hydrogen. We need to know what the pressure of the hydrogen is. All right, so now we've got, this is our pressure. The volume.
Is that the second line, like,
1 atmosphere. This one here? This line?
Yeah, is 1.00?
Yeah, 1.00 atmospheres. That I'm getting that right here. Here. That's where I'm getting that. The volume of the gas is 246 milliliters. The volume is 0.246 liters. The pressure now is, we've compensated it, 0.9687 atmospheres. The temperature, I guess we can assume, is this temperature. We're doing this at 25 C. And now it says calculate the number of grams of sodium used in the reaction. Well, we're going to calculate N, the number of moles of hydrogen right now. And then you're going to convert moles of nitrogen back to moles of sodium and grams of sodium. Okay, so this uses Dalton's law and the ideal gas law at the same time. Only to get this right pressure. That's problem 26. Okay. All right, we didn't take that to completion. All right, number 25 is Dalton's law, partial pressures. A mixture of gases contains 0.3 moles of that, 0.25 moles, 0.29. The total pressure is, okay, now 25, I'm sorry, I'm jumping in the middle of things here. But what you'll find on Dalton's law of partial pressures is that the,
What's the formula for it?
yeah, the formula for here is that the pressure of methane is going to be equal to the mole fraction of methane times the total pressure. So what is the mole fraction? You add these up. That's your total moles of gas, and the mole fraction for methane is going to be 0.31 divided by that total. That's the equation there. 0.31 plus 0.25 plus 0.29. I'll tell you what, let's omit 25. How's that? Omit that. If you can get 26, yeah, and this is another stoichiometry one with gases. This number 25 here, don't make this too complicated. Number 23. Is that number 23? Don't make that too complicated. You're being given an equation right here. 2 moles of NO yields 2 moles of NO2. You're at STP. What is the volume in liters of the NO2 produced? Nine liters. Oh well. Let's just leave that. Okay. Yes. Now I'll tell you what. Do everything but the number 27. Try to do everything but 27. I haven't explained that. There's a couple things I haven't explained. But this is one I will explain. How you deal with a non-ideal gas. I'll explain that right at the beginning of class on Thursday. And then we'll collect this homework assignment. How many more are there after all of that? I think it ends right there, doesn't it?
Yes.
Okay, so we end right about here. I have some more. You can see I didn't give you a bunch more problems. So we'll do 27 in class on Thursday and then collect this, and then I'll be handing out the Chapter 5 group work on Thursday.